What is the average rate of change? I've highlighted that here. And bonus points if you guys remember that when you say average rate of change, we're really just saying slope. This is a big idea in calculus. And I want to draw you a picture. Let's pretend we have some curve. This is not negative 5q squared, by the way. This is just some random curve that I'm drawing here. And I said, what's the slope at this point right there? Right? You can imagine a tangent line would look something like this. Okay, so it has some kind of negative slope. But you might remember another equation for slope, which is the following. Slope equals y2 minus y1, that's our rise, divided by x2 minus x1, that's our run. So it's rise over run. So you might think, okay, well, how do I figure out y2 and y1 if I'm just looking at one single point? This is not average rate of change between 2 points. It's average rate of change for a single point. So I think the logical way to go would be to pick 2 points near it and draw a line between those and figure out its slope. But if you notice, those are close, but they're just a little different. And it's not too accurate to pick 2 points that are far apart. For example, if I went further apart, say a point right here and a point down here, now this is just completely broken, right? That's not accurate at all. So the idea is we want to get as close as possible to that point of interest as we can. So we're going to pick 2 points that are really, really very close to it, like right here and right here. And when we do that, our estimation of the slope is going to be very, very accurate. So let's go ahead and pick 2 points that are very close to q equals 3. I'm going to say, let's see, how about x1 equals 2.9 and x2 equals 3.1, right? We're on either side of 3, very close to it. And now I just need to figure out what y is in each of these cases. So y1 is going to be f of 2.9. And I know the letters are different in that equation. Don't worry about that. That just means we're going to plug in 2.9 into all the variable places, okay, as I'm doing here. Now I pre-calculated these numbers to save a little bit of time. And what I got was f of 1, or sorry, y1, the first point, located at x equals 2.9, equals negative 52.65. And you can run this through a calculator, see if you're doing it the right way, but I think you'll find the same answer. And y2, according to the same method, would equal negative 59.45. Okay, those are a little ugly, but I'm just going to plug those into my slope equation, like so. I'm going to say slope equals, we're going to take y2, that's negative 59.45, minus y1, that's a negative sign, so I'll be a little careful and write this in parentheses here, all divided by the difference in the x's, which was 3.1 minus 2.9. And if you crunch that through the calculator, you're going to get negative 34. That's our answer. That's the slope right at that point. Now, you could say, well, maybe you didn't go close enough. Maybe I should try some decimals like only 0.01 away from the point. And that's a great idea to try out on your own. I'm not going to do that here. This happens to be a very special case. We're dealing with a quadratic function, and the quadratic function is actually a little more forgiving than usual. A lot of functions want you to get extremely close, like 0.0001 away from that point, which is a little bit of a pain with the decimals. But quadratic functions give you a little bit of slack. You don't have to get quite right up to it.